Okay, so what I would like to do now is I would like to make use of the four-dimensional version of the divergence theorem. And it says that the integral d4x of d mu f mu, so that's the quantity that we want to study. This is over the whole universe, V. This would be equal to an integral of f mu ds mu over the boundary of V. And ds mu is this integration measure over the boundary of the surface of the universe that we've just been discussing. And dv would be the 8 sides that we've just been discussing. So let's just write out what this would look like. Okay, so for the very first side, at t is equal to t, we said the only element of ds which does not vanish is when mu is equal to naught, the time component. That is just because there's a t hat sitting there. So that integral will look like an integral over dx, dy, dz. Each of these runs from minus L up to L. And then we would have f naught, only the naught component of ds is non-zero, to be evaluated at time t, and then at x, y, and z. Good. And the ds naught, the dx, dy, dz, is what's sitting there for the integration measure. Okay? And then if we look at the second side, we'll have a minus. We again have a dx, dy, dz. So let's put that in, dx, dy, dz. By the way, the minus sign has come because this measure element has got a minus t hat in it. Because it's t hat, again, this is the time direction. So only f naught plays a role. We now have to set t equal time equal to minus t and x, y, and z range over whatever they like. So there are the first two terms, and maybe let's just color code them. These correspond to the blue terms, and that's why we are indeed integrating over Euclidean space. Okay, now let's go to the next term. So what do we have here? We've got set x is equal to L. So we're integrating over t, y, and z. That's what sits inside the ds. So we'll have an integral over t, over y, and over z. And this is minus L to L and minus t to t. Now, ds has got an x hat in it, which means it only has a 1 component. Only ds1 is non-zero, so we'll only get f1 contributing. This will be at t. X has been set equal to L and y and z. Okay. When we look at the next side, it'll be minus because we've got a minus x hat appearing. But then again, inside ds, we have to integrate over dt, dy, and dz. And again, we integrate them over the whole side of the box. And again, inside the ds, only the x hat component is non-zero. So we'll have an f1. We will have t. Now x is set equal to minus L, y, and z. And these two are the first two terms in the green integration region. Okay. Now, next, let's take a look at the side at y is equal to L. So for that side, we have to integrate over t, x, and z. So let's put that in there, t, x, and z, from minus L to L, minus t to t. And now take a look at ds. There's a y hat appearing, so only ds2 is non-zero. So we'll have f2, we'll have t, we'll have x, and y is set equal to L, and then we've got z. The next side at y is equal to minus L has got a minus y hat, so we need to change the sign. We again are integrating over x, z, and t. So let's put in those integration regions. Good, there they are. And if you take a look at ds, only a y hat appears, which means only ds2 is non-zero. So this will be f2 t x y is set equal to minus l, and then also z. Good. So those are the next two terms, and we only have two terms left. Okay. Sorry, I know this is painful, but let's just do it. So we've got plus. Now take a look at the second last side, the side at z is equal to l. We need to integrate over t, x, and y. So there is the integral over t. There is the integral over x. And here is the integral over y. And when we take a look at ds, there's a z hat, which means that only ds3 is non-zero. We've got t, x, y, and z is evaluated at l. And now for the final side, there's a minus z hat, so pick up that sign. We need to integrate over t, we need to integrate over x, we need to integrate over y. The ds only has a z hat in it, so only ds3 is non-zero, and z is evaluated at minus l. And this is the sum total of the terms that appear from the integral d4x of d mu f mu over the entire box. Now, we know the fields vanish at spatial infinity. So fields vanish at spatial infinity. Well, these integrals, that one, x has been set equal to L, so that is spatial infinity. This is x is minus L at spatial infinity. Y is L, y is minus L, z is L, z is equal to minus L. So all of the green terms vanish immediately just because fields vanish at spatial infinity. Now, what about the two blue terms? Those are evaluated at the initial time and the final time, but any spatial location. There are situations where the field need not vanish at the initial time and the final time. A good example that we're about to see is for the Euler-Lagrange equations. But in that situation, the initial configuration is fixed, the final configuration is fixed, so the variation of the field on the initial surface and the variation of the field on the final surface both vanish. So in fact, the terms that we get from the integration by parts in the Euler-Lagrange derivation of the equations of motion, those will also vanish at the initial and final times. In ordinary quantum field theory, what do we usually do? Well, we start with the vacuum, and then at some later time, we act with fields that create particles. Then at some much later time, we act with fields that destroy the particles, and we land up with the vacuum again. So we start with the vacuum, we land up with the vacuum. And again, these are situations where you've got no distribution of particles sitting there. They've all been destroyed. So in this situation too, we arrange that, let's say that the terms at t is equal to plus or minus t also vanish. So sometimes we need to be a little bit more careful about these terms, but we typically set things up so that those terms vanish too. So that would vanish, that would vanish. We'll see examples of this. So that at the end of the day, our conclusion is indeed that this integral vanishes. And that's what we wanted to prove. We wanted to show that the surface or boundary terms vanish and can be dropped. I'll often be dropping the surface terms, the boundary terms. When I do that, my justification is precisely what we have discussed here. Good. So now we can move on to deriving the Euler-Lagrange equations themselves.